Hello community! Today we talk about a unified theory of AI reasoning, the latest research, and we go for a geometric edition. Let's have a look. Welcome to my channel, Discover AI, the latest research, and this is part 2. Because the task was look at the latest publication here, 6 brand new papers from all of these beautiful institutions. Now, in my last video, we did the top 3, and now we have another 3 versions that we have to do. The latest research from UC Berkeley, Nvidia, Microsoft, Peking University, Harvard University, University of Southern California, and Tsinghua University. So let's jump into this. And yes, of course, I do have a process behind it, because if you look closer and if you have already looked at the paper, you'd know that this describes here the state, the process, and the learning dynamics of AI reasoning. So what is the latest insight? Okay, here we have it. Publication REMA, a unified reasoning manifold framework for interpreting large language model. And you might say, hey, this is absolutely beautiful. And the authors tell us, understanding how LLMs perform complex reasoning, and in particular, their failure mechanism is a challenge, especially if you want to have here an interpretable AI. And to provide now a measurable geometric analysis perspective, they come up here, or they further elaborate on the idea of a reasoning manifold, which is simply a latent low-dimensional geometric structure formed by the internal LLM-specific representation corresponding to all correct reasoned generations. You see, it is a rather simple idea. You do have correct reasoning. But it is not a random walk here in this high-dimensional activation space if you look at your tensor structure in the layer of your transformer. But now it becomes a structured journey along, and now, surprise, surprise, a low-dimensional highway. So the core idea is that for any given task, all internal representation in the hidden state generated during the correct reasoning process of our LLM form a new geometric mathematical structure now in an embedded lower dimensional space. And this is the reasoning manifold. And this is embedded within the high dimensional activation space at each layer of our transformer architecture. And you can think about this of the golden path for the collection of all valid thought processes that the LLM has learned. And since the true manifold is unknown, it is of course approximated by a point cloud of correct representation. So let's work with this. So there are 2 steps we're going to look at, now the researchers looked at, and this is quantifying here the failure mode of AI reasoning as now a geometric deviation in a high mathematical space, and then localize the divergence point, where do things go wrong. And then we have, if you want, a microscope to analyze exactly where the reasoning process goes off. So what they did for the point A, quantify here the failure as a geometric deviation, it is so easy, it is so simple. Now, they just calculate its deviation distance. If you want, you can go with a metric space Euclidean distance to its k nearest neighbor within the set of correct representation. You have a baseline, you compute here the average internal distance. Yeah, simple. And then, because you have this, now you can go here and look for the divergent point. No? Because you just have to look for representation deviations in the geometric space that become statistical abnormal. Beautiful. Now what the REMA does, this reasoning manifold, is it connects now the abstract reasoning failures of our LLMs to measurable geometric deviations in the representation, providing us with new avenues for an in-depth understanding and especially a diagnosis of the internal computational processes. So you might say, hey, this is simple. Well, in fact, it is not that simple, because this builds on an intensive mathematical knowledge. If you would like to learn this, I would recommend here this paper, Testing the Manifold Hypothesis. You see, it's from 2013, but this is essential. And they say here the hypothesis is that the high-dimensional data tend to lie in the vicinity of a low-dimensional manifold. This is the basis of manifold learning. And this is here to develop an algorithm for testing the existence of a manifold that fits a probability distribution supported in a separable Hilbert space, only uses, and you get it. So what we're doing, we're saying, okay, this new idea of REMA is kind of a quotation mark natural extension of the widely recognized manifold hypothesis, C 2013, from machine learning now to the process of LLM reasoning. We applied now to the reasoning process, which should allow us to translate here the abstract notation of correct reasoning traces into, we convert them, and analyzable geometric objects. Isn't this beautiful? We have now a look at the sorts of an AI system, not as an abstract view on the activation pattern in our tensor structure of the layer of a transformer, but we can analyze it now as a geometric object. Now, it is, again, as I told you, not that easy, because if you read now the second paper I would recommend by Ghosh here from April 2014 about representation learning, they say the manifold hypothesis posits that meaningful data variation are often confined to low-dimensional manifolds embedded within a high-dimensional space. It is not as trivial as you think. You have your deep learning Boltzmann machine autoencoder. Have a look at this, and then you have to read the third paper. This is now from April 2021 about the intrinsic dimension of images and its impact on learning. This is here University of Maryland and University of Texas at Austin. They define now here, especially done here for images, for natural images, which exhibit here a low-dimensional structure, an intrinsic dimension of their activation during the specific task. And they say the intrinsic dimension now, if you want, where the thinking is happening, the dimensions are significantly lower than their all available mathematical space. And then you read here from February 2024 the information of large language model geometry. And now you see Department of Mathematics, Tsinghua University, and Shanghai Jiao University. And why I love this paper, the authors here say, the analysis of the representation entropy further connects now the information theory with LLM geometry, exploring here the scaling laws by relating entropy to the model size. But you see, we are all here on the geometric interpretation. And now let's come to the result of this new study. And you see, it is just a continuation of a research that started more than 10 years ago. And now we can build on this, and the authors build on this, and here are now the results. So on the x-axis, you have here the layer IDs of your particular LLM. On the first, you have here the QN, and then in the second row, you have here Llama 3.2. All the results show here the same. They show that all intrinsic dimension are significantly lower than the original hidden space dimensionality. Look, the intrinsic dimension is here 6, 8, 10, 12, 14. And now for the moment, it is not really important if we have a correct reasoning or an incorrect and error reasoning path here in the reasoning trace. Just look, the thinking, if you want, in a very simplification, is happening in a mathematical space that is not the complete hidden space dimensionality. It is done in a tiny, tiny little low-dimensional mathematical space, and you have here the intrinsic dimensions here. Now, the mutual information is relatively high in the early layers, as you see here, and gradually decreases here the deeper you go into the layer architecture of your transformer architecture. This is absolutely interesting. Why? Because this provides here a strong evidence that the internal reasoning process of our LLMs that we look at, both successfully and failed, we don't discriminate now for the moment, tend to operate within a low-dimensional subspace. So the complexity reduces massively because we don't have to look at a 4,000-dimensional mathematical space, but a really tiny low-dimensional subspace where the AI is reasoning. And this now validates the rationale for using here the manifold analysis, the papers I showed you starting at 2013, 10 years ago. So you see, we now validated that this is a correct way, a correct rationale for analyzing here the thought process of our latest LLMs. Now, to actively intervene, because we want to change something, if we see there's a failure, we want to optimize the system and improve our LLMs, is by designing now new novel regulatory terms that encourage the model to learn a reasoning manifold with more desirable geometric properties. Or, if you want, if you think about a Kullback-Leibler divergency term now in this subspace complexity, by employing here a technique like to pull back the deviating representation onto the learning and the reasoning manifold to correct and minimize error. What a beautiful new idea to transform the learning process in a geometric problem, a shape problem in a high-dimensional mathematical space, and then say, you know what? This could be the way to further improve the model performance. But this was just paper number 1. Let's have a look at paper number 2. And yes, now we go from a manifold representation to a graph representation. And yes, it has something to do with a geometric addition. Of course, this is why I selected it. Now, here we have the authors from UC Berkeley and Nvidia. So what they do, also September 26, 2025, they have here GSM-AGENT, understanding here the agentic reasoning using here controllable environments. So what we are talking about? They say we here, Nvidia and UC Berkeley, we want to analyze the agentic reasoning patterns. What are those reasoning patterns? Where are they? What is happening to them? We want to see them. We propose here, they ought to say, a concept of an agentic reasoning graph. So now they also go to here, and they didn't know anything about the other studies, so this is just because I selected these studies because they have something in common. They go now for a graph representation. So they cluster here the environment's document embeddings into the nodes, and then map each tool call to its nearest node to build a reasoning path. What a genius idea. Simple but efficient. And they say, you know what? LLMs are increasingly deployed now as pure agents, of course, with memory and tool calling capabilities. So LLMs deployed as agent, the agentic reasoning, so this means the ability to combine tool use, especially here a search and a reasoning ability, becomes critical. And they say, okay, let's develop now a benchmark especially for this, a novel benchmark, GSM-AGENT, where an agent is required to solve simple reasoning problem, but is only represented with the question in the prompt without a promise. So it has to proactively collect the information using the tool for a reasoning process. So you see, it's like a higher complexity reduced to lower complexity, but now we say, okay, I give you only the question and the ability to use tools, so you have to find here all the necessary information to solve the task. They did it here on a very old friend. This is here on the benchmark we know for a lot of years. And to say, okay, let's test this here in a mathematical way. Great. Evaluation sees only the question and they use for tools, and they have a search tool and a next page tool. This is it. It couldn't be easier. So they start to build now their data set. So they go here with a known benchmark and they say, okay, the data processing is now in the following way. I understand here, this is the question, and then I have here the premises to solve this, and then I have here the document generation. All the documents that you need, and they did this, not of course by hand, by humans, so they used here Claude 3.5 Sonnet as the default LLM to facilitate here this data processing and data pre-processing. By the way, if you want to see the performance of the brand new Sonnet 4.5 and that their reasoning exposes here a major flaw, have a look at my latest video. Now, what were the results here from Nvidia? They told us here a frontier model like a GPT-5 loses roughly 33% on absolute accuracy doing agentic reasoning, whereas some models like the old DeepSeek version 3 loses up to 80% in accuracy. Something is massively going wrong here with agentic reasoning. What is happening? And the authors tell us the result demonstrates a clear and consistent gap between the static and the agentic reasoning, now in a clearly defined and controllable environment in a setting where we can modify the parameters and really isolate the root cause for the failing of agentic reasoning, even with a GPT-5. And I know you're going to say, but wait a minute, GPT-5 is perfect, no? All the marketing materials by OpenAI say GPT-5 is just perfect. Well, welcome to reality. Now, to go this step and understand what the authors are doing, you need to read another paper. And I would recommend this paper to you by University of Tokyo and Google DeepMind. This is here from June 2025, The Topology of Reasoning. You see, the complexity of those papers are so high, they're so interwoven, that sometimes you need to go down this rabbit hole and understand also the topology of reasoning, understanding here large reasoning models through the reasoning graph properties, because this has already been explored and we already have results we can build upon. So here in this paper from June, my goodness, already months ago, they introduced the notion of a reasoning graph. And this is what we're going to use here in the latest publication. And the reasoning graph is extracted by clustering the hidden state representation at each reasoning step. Now you're familiar with this. And systematically analyze three key graph theoretic properties: the cyclicity, the diameter, and the small world index. And we do this here for benchmarks that are really, really old. So they are absolute familiar benchmarks. So you have here the question, the base model, the reasoning model, and you have here the constructor here of the reasoning graph. Plus, in this paper, they have a graph theoretical analysis of enhanced reasoning on graphs. And they show you here exactly how to do the extract the reasoning graph from the LLMs if you have the different layer and the reasoning step here. So if you're interested to have a deep dive, I highly recommend this paper. But what are the results now of the latest paper here? If you would know all of this, and we are familiar with all of this technique, what is now the latest insight? Now here we have the numerical result, and you're going to say, okay, great. Any better visualization? Yes, of course. Here we go. So on the x-axis log, you have here the number of tool calls that the system needs to solve the task, and the accuracy, and we go from 0 to 60, maybe 70% here. GPT-5. Kimi K2, Llama 4, almost flat at 20%. This is the reasoning performance with tool calls of your model. And now you have one question, and I know because I had the same question. Hey, what drives such big differences here in the performance across our models? A Llama 4 to a Kimi K2 or a GPT-5, given that we are operating in such a simple environment. How is this possible that not all the models go to, 95% accuracy? Why we are stuck here at below 20%? What is happening? And they said, okay, so let's build this agentic reasoning graph. Let's try to have here a mathematical tool to understand what's going on. And they say this is now our core analytical innovation in this paper. Because we want to understand here the agent's search strategy, they abstract it into a graph representation. You see, whenever we cannot go further, we just think about, hey, can I find another perspective, another way to view this problem? And they say, yeah, graph representation. What are the nodes? The documents in the database are embedded, and the embeddings are clustered using k-means. Beautiful. And then we have the path. So each tool call made by the agent is mapped to the nearest nodes. We have a cluster centroid in the embedding space, and we have a sequence of tool calls. Thus, we have a discrete path here on this graph. Couldn't be easier. And now they say, we know from, at least from reinforcement learning, that we have here a particular behavior of our agents, and it is here about a very delicate equilibrium between the exploration of all the new possibilities, the exploitation of the known facts and of the known correct pathways, and this is now really brand new, they discover there's something new like a revisit, a returning to a previously visited node after having gone somewhere else. So you have to return to your reasoning base. And this is something I've never heard before. And they tell us, hey, our main key empirical finding of the complete paper is that there is a strong positive correlation between the revisit ratio and the overall task accuracy, while all the other patterns show weak or negative correlation. So in the reasoning process, they tell us if we do this and we build a new graph representation and we have the known exploration and the known exploitation, there is now a new piece. And this is here, revisit your logic reasoning base. Come back to base and then go out and venture for new information. And now the authors tell us the ability to integrate new information and then consciously return to a previous context to re-evaluate it is a hallmark of a successful agentic reasoning. This is the main insight they found in this study. You have to come back to base. Now this third paper, and we will do the summary how those three papers belong together, but first we have to look now at paper number 3. And paper number 3 is from Microsoft, Peking University, Harvard University, and University of Southern California. And guess what? It's another graph representation. But now we learn about the benefits and pitfalls of reinforcement learning for language model planning. And they say, okay, so now we investigate here the reinforcement learning mechanism, the benefit and its limitation in the current form of end of September 2025 through a lens of a graph-based abstraction, focusing here on policy gradients and Q-learning methodologies. And they tell us, oh boy, there's a big difference between those two, and you better choose the right methodology. So let's have a look at this one. And they tell us, for humans, first they say, hey, for humans it is so important to do the planning, it's a fundamental cognitive construct to organize tasks and formulate complex solutions like mathematical proofs, and yes, humans. And then they say, and what are AI systems doing? Identical to humans, or where are we? And they say, despite recent successes, the theoretical basis underlying here the reinforcement learning advantage over, let's go with supervised fine-tuning, in the planning task. And important, they only focus here on the planning. And the limitations in the current reinforcement learning methods remain to be established. And they say, and we set out to do this. So we build now the real understanding, the real theoretical basis for RL. So what do? We have a look again at the fundamental limitations of supervised fine-tuning in the planning phase. Then we focus here on the behavior of reinforcement-based learning dynamics, especially looking at policy gradients. And then we analyze the Q-learning. So there is now the main, if you want, sentence. And you would say, okay, so let's have a look. The mathematical analysis of this paper. Please read the paper yourself. It's really a beautiful paper. The mathematical analysis of the learning dynamics shed light on the phenomena observed in practice. We know that supervised fine-tuning tends to memorize, while reinforcement learning promotes here the generalization. And here within RL, we have here our policy gradient methods often suffer from the diversity collapse. I will explain this in a minute. And the solution is a Kullback-Leibler regularization helps mitigate the diversity degradation, albeit at the cost of a reduced accuracy. And we know this. And we say, okay, what's new? Now, if we focus in on the diversity collapse phenomenon, this simply means that the model output diversity steadily declines throughout the training and continues to diminish even after achieving a 100% training accuracy. You might say, hey, something is going massively wrong, no? Because we know the formula for the policy gradient. Yes, of course. And we know here the Q-learning. I have, I think, 5 videos on Q-learning. And so you say, what is this new stuff? So supervised fine-tuning memorizing here the co-occurrence relationship in the training data set. And then you say, but for the path planning capacity, here, let's look at the policy gradient. We go with PPO from 2017 or GRPO or whatever you have here. We have a convergence here of the policy gradient without a Kullback-Leibler regularization, but we do have a diversity collapse of policy gradient. So this is something that is really the main problem. And this diversity model collapse phenomenon can impair here a model's ability to generalize to new unseen facts and data. If you want to see this here, the test accuracy, the training accuracy, and then the output accuracy, the output diversity goes down. And you see here the influence of a Kullback-Leibler divergence. Great. So what do we do? They say, even after achieving a 100% accuracy here, the training dynamics of a policy gradient continue to push the probability distribution towards a single one-hot vector. So this means here in the reasoning process, our large reasoning model finds one correct path for each problem and over-optimizes for it. losing now the LLM the ability to generate alternative solutions that might be better, and the whole LLM reasoning becomes brittle. You see this beautifully in my latest video where I show you here Sonnet 4.5 here. The reasoning exposes here some major flaw. This is happening. It converges on a one hot vector. It finds one correct path. It's an incorrect path, but never mind. This is all that the system Sonnet 4.5 finds. And then it over-optimizes for this. It adds this path one time, another time, a second time, up to 5 times the identical single path, and it has no reasoning diversity. This is the major flaw from Sonnet 4.5, and you see it here explicitly in my new video. Interesting. Those two things come together. But we want to have a solution. We want to find better models. So what we do? The authors tell us, you know what? We analyze now the Q-learning mechanisms for the planning phase of an LLM under 2 different reward designs. And they show, and this is not a result if you want, that a stepwise process reward enable the convergence of the whole process and preserve the diversity of the outcome solution, which is and remain valid under off-policy sampling. Whereas if we go here with the different design of an outcome reward, the whole system collapses into trivial solutions. Remember what I told you about Sonnet 4.5? Outcome rewards collapse to trivial solution and fail. So therefore the authors conclude, compared to the policy gradient methods, the Q-learning that is hardly anywhere can operate off policy and better maintains the output diversity. What a nice insight, and we will use it. So you see, this is why here in the video I choose here these 3 videos here. They also go together because they describe here the state of the reasoning, they describe here the process of the reasoning, and they describe here the learning dynamics of AI reasoning. So thanks to UC Berkeley, Nvidia, Microsoft, Peking, Harvard, and you can see it in a different perspective, and this is the fun in AI. Have a look at it from all the other perspectives that you can imagine. Go geometric, go biologic, go whatever you like. Transform, map it. You have so many actions to do. So REMA, the first paper, examines here the static of cognition. The second paper examines here the process of cognition. And the last reinforcement paper examines here the learning dynamics of cognition. Or you said, hey, the learning dynamics shape the internal state space, which determines the agent ability to execute a successful reasoning process. And now suddenly all 3 papers are connected. And if you read those papers and suddenly somewhere a little voice in your brain tells you, hey, wait a minute, all those papers you read, there is a connection on a deeper level, like this sentence. And this is the beauty if you do AI research. There's so much waiting for you to be discovered. So what are the main insights? Let's do this. Insight 1, the geometry of sort extends to the geometry of action. The diversity collapse is the enemy of a robust reasoning in the agency itself, and a unified framework for diagnosis, explanation, and intervention is hidden within these 3 papers. So if we combine these 3 frameworks now into a powerful cycle, and let's say the task is an agent fails at a particular task, great. So what we can do now with our new insight, with our new knowledge, we have an answer to what and where, to why does the agent fail, and how to fix the failing agent. Let's have a look at this. What and where? What we can do now is analyze the trajectory of the agentic reasoning graph. Did it fail to find a key piece of information? Did it fail to revisit a node after getting the new context? Those are suddenly questions that are important in the understanding, and you can use REMA to analyze here the internal state corresponding to that failed action trajectory. You can even, if you want, pinpoint the exact layer where those representations first deviated significantly from the manifold of the correct reasoning, because this is a low-dimensional subspace. How beautiful is this? Let's come to the why. Now you can now ask, hey, was this model trained with supervised fine-tuning? Because then the failure is likely due to an out-of-distribution path it couldn't have memorized. Or you might ask, hey, was it trained with a policy gradient? Because then the failure might stem from the brittleness caused by the diversity collapse. It encountered an unexpected state and couldn't recover because its policy was too narrow. There was no new strategy. It was always coming back to the same solution and it just applied it and it fall into this hole of a single solution. And then there's the beauty of how to fix it. And this is why I do this video. What can we learn from this? So how can you fix this? Now, the specific diagnosis here dictates also the cure. If the problem is a missing revisit skill in the reasoning trace of your LLM, design prompts or fine-tuning the data that explicitly demonstrate that this pattern is important, inspired here by the paper of the GSM-AGENT. Or if the root cause is a diversity collapse, the theory now suggests that switching here to a Q learning paradigm in reinforcement learning with a process reward could build a more fundamental, robust, and diverse model. So you see, by combining the geometric, the agentic, and if you want the theoretical lens of reinforcement learning, we move now from observing the failure modes and the failure symptoms to diagnose now the disease, if you want, and even go to prescribe a principal cure for this. And I love this integrated perspective. If you read 10, 20 papers and you start to feel, hey, there is a connection somewhere. And this is the beauty of AI. So this, like this video today, kind of an idea. Maybe it sparks here the wish, building here a future AI that is more intelligent, more reliable, and a real understandable AI system. And you know, just talking about this, and the video is now ended but let's just continue thinking, né? Because this reasoning manifold is not an internal mathematical construct, né? Because for an agent, the sequence of a correct action described now in the GMS agent can also be seen in this new paradigm as an action manifold, no? So a failure is no longer just an internal representation deviating from its low-dimensional manifold because, yeah, okay, I think you got the idea. Just build on this, become better. Have fun with AI. Thinking is amazing. And of course, if you subscribe, I will see you in my next video.